Let's go on page 25 when we're done. Guys, hey, do me a favor. You two switch places. I'm tired of them already. Yesterday, we talked about rate of change with linear and quadratic functions. So today we're going to talk about it with polynomial functions. Yes, a quadratic is a polynomial, but we're just talking about like all the other ones as well. So your definition of polynomial functions looks like this. This is a textbook definition. A polynomial function is any function representation equivalent to this analytical form, which looks like a nightmare, right? And it's okay, we don't have to actually write it out. That's why it is written for you. But I'm also not going to shield you from that stuff. You might find yourself in college teaching yourself math from a textbook, and if all that stuff makes you freak out and your brain shut down, you're out of luck, okay? A lot of stuff that is written generically for math looks way worse than it actually is because we have to use variables to generalize things, okay? But if I have a function, let's say that I have h of x equals 4x to the fourth plus 5x cubed, oh, that's cubed, okay, hang on, cubed, plus x minus 3, something like that. That's a polynomial, right? That's not new to you. You've done lots of things with polynomials. The reason this looks so crazy is because we have to take into account that our leading term could be, you know, 5x to the 9 millionth. I mean, our exponents could be whatever. But as you see, this x to the nth here, you got n and then n minus 1, n minus 2. So when things are in standard form, like it should be, n would be 4, n minus 1 is 3, and then you go in order down the line. That's what the little exponents mean, all the way down to a number times x, and then just a number, just like this right here. And then our little subscripts are just the coefficients. That's all it is. But it does go on to say n is a positive integer. So I can't have 4x to the negative third. That would not be a polynomial. You can have that, it's just not a polynomial. Or 4x to the 1/2 power, not a polynomial, all right? Also, all of the leading, or all the coefficients are real numbers. None of them are imaginary numbers. And the first one is non-zero. So notice here, I'm missing the x squared term. That's because the coefficient would be 0. I have 0x squared, so it zeroes out. I don't even put it there. That's fine for anything except the first one, because we have to have a starting point, right? So here, our leading term, not necessarily always the first one, but the one with the largest exponent on it. In this case, the term, okay, and your vocabulary here is important. The whole term is a sub n times x to the nth. That's the leading term. The degree of the polynomial is the exponent that's in the leading term. So that's just n. And then your leading coefficient is the number that's in that leading term. So in this case, it would be a sub n. Okay. Any questions about that? We good? That makes sense? All right? Not that bad. All right, so now we're going to look at these. This should hopefully be pretty simple here, this first part at least. Find the leading coefficient and degree of the following polynomial functions. Okay, so this is my leading term. So what's the leading coefficient? 3. And the degree would be 4. Okay. Yes? All right. On B, what would the leading coefficient be? -7. Good, because it's not 12. This is my leading term, even though it's not first, because it's got the highest exponent. So my leading coefficient is -7, and the degree is 3. Okay. What do you think the leading coefficient is in C? 4. Okay. What do you think the degree is? Okay, yeah, not 1. I hear that all the time. If it was 1, it would be 4x to the first. That's not what I have here, right? Just trying to make a 1 there. All right, so what if I had 4x to the 0? What's anything to the 0 power? 1, and that's what would give me 4. So we don't put x to the 0 because it doesn't really make a whole lot of sense, but your degree is 0 there. Okay, everybody good with that? That makes sense? Okie dokie. So now we're going to talk about some attributes of these graphs. right? And we'll get deeper into a lot of this stuff in the next week or so. But there's still some things we can do to figure out other things about our polynomials. So you don't have to write this down, just stay with me and it'll make sense. If I have an even degree, so my polynomials are either even degreed, odd degreed, or it's a 0 degree, and 0 just doesn't matter. We look at even and odd. If I have an even degree polynomial, the end behavior, okay, lots of things going on in the middle, but the end behavior is going to model a quadratic, okay, and we're like quadratic experts, right? My quadratics, the parent function opens up, up. What would cause my parent function to change and go down, down? Negative. If I have a negative leading coefficient, that's what reflects it down, right? That makes sense? Okay, so it's either up, up, or it's down, down. It's like it's not going to do anything else because it's a parabola, right? And again, we're just looking at the ends, okay? The middle stuff changes after it's not a parabola anymore. So if I have an even degree, I know it's a positive leading coefficient. I'm going to start up here. I don't know what the rest of this stuff looks like, but I know it's going to end back over there, okay? And we'll worry about the mess in the middle later. Right now, we're not concerned with that. We're just kind of concerned with the end. And if you took Algebra 3, some of this should look familiar from when you did, you were sketching polynomials, okay? Because that's something that you do in Algebra 3. And if you haven't, it's okay. Like I said, we'll have some detailed stuff about this, but we'll be able to get through a little bit of it today. If it's an odd degree, then it models a cubic. The end behavior does. So they're opposite. And for a cubic, you need to know what the parent functions look like so you know which way it's pointing when it's positive. And then if it would reflect, if it was negative, it would go the opposite way. But for an odd degree, they're always opposite. So if it's an odd degree, positive leading coefficient, then I know it would start down here. I don't know what's going on here, but then I'd have to end up there. Okay? Does that part at least make sense? Okay. So next thing I want to talk about before we go back to the notes is, if I have a quadratic, how many possible zeros, x-intercepts, roots, solutions, whatever, how many could I possibly have? I could have 2. If I had 2, it might look something like that, right? Could I have just 1? Yeah, and it could look like that, right? Could I have 0? Yeah, and it could look something like that, right? So I could have 0, 1, or 2, but I could have at most 2 because it is a second degree polynomial. You with me on that? Okay. So here, we're not going to dig deep enough into this 4th degree polynomial to figure out exactly how many zeros I have. We could, we just don't really care right this second, so we don't need to do that. But what I can do is this. This is an even degree polynomial. I have a positive leading coefficient. So my end behavior models that of a positive quadratic, right? Up, up. And really, if I just know I start up, then everything else takes care of itself. And I'm gonna make 4 intercepts. So if I start up here, I'm gonna have to cross the x-axis 4 times. So I'm gonna go 1, 2, 3, 4, like that. And because I was doing 4, I ended up, up anyway. You with me on that? So I can draw that. I can sketch that. It's not a drawing, it's a sketch because there's a whole lot wrong with it, I'm sure. It probably, if we were to actually graph that one, it probably looks way different. But the things we care about right now are still true and we can use it, all right? So little sketches for a lot of what we do can be very, very helpful. So what this shows me is I could have at most 4 intercepts. Maybe I really don't. But not only does it show me that, it shows me my turning points. Because in order for me to cross through the axis to get my 0, I had to come down here. I hit the axis. I had to turn around and go back, and then turn around and go back, and then turn around and go back, right? And so I have these 3, what we'll call turning points right now. So since it's a 4th degree, I have at most 4 roots or zeros, and I have up to 3 turning points. Yes, it is just the degree minus 1, but again, when we were asked other things, the little sketches come in handy for a lot of stuff. Okay, we good? Questions? All right, so now when I look at B, and I'm going to do a little sketch. This is an odd degree. Okay, remember this is what a cubic looks like, but this is a negative leading coefficient. So instead of down, up, This starts up and it should end down. Okay, so if it's a third degree, I have at most 3 intercepts. So I would start up here and I'm going to cross 1, 2, 3 times. And by doing that, it automatically ends up down, as long as I know where to start. So on this one, I can see that I have 2 turning points. So this would be up to 2 turning points. And it's up to, because if you look at your parent function doesn't have any. It's going the same direction the whole time, right? We don't change. Questions at this point? Pretty much, yeah. And so here, I want you to sketch what that one would look like. What's another way to talk about g of x? Y. So this is the same as y equals 4. Is that a horizontal or a vertical line? Horizontal. That's y equals 4. We took a lot of liberties with those other two. And like I said, if we actually put those in something, we graphed them, they'd have some properties in common that we can talk about, bless you. But they probably wouldn't look exactly like what we have. That is that, no matter what. Okay, and that's a line you got to be able to graph for sure. How many turning points do I have? None, yeah. So no turning points. Okay. Questions at this point? Good. All right, so the next thing that we're going to talk about, is not something that's new to you. The word extrema might be new to you, but it is just the plural of the word extreme. We could say extremes in plural that way, but extrema is it's just plural, all right? So the extrema of a graph are the minimums and maximums of a function. And I know you've talked about maximums and minimums. There are 2 types of extrema, but both of them have 2 names, and we have to understand both of them. They can be used interchangeably. You might have one question that uses one and the next question uses the other. So it's not like, depends on, who your teacher is, what their favorite word is. You'll just see them both all the time. So the first one we have is the relative or local extrema. Okay. So a polynomial has a relative minimum or relative maximum where it switches between increasing and decreasing. It's where your turning points are. If I'm going to change from increasing to decreasing, I have a local or relative maximum or minimum. And then in pre-cal, we also talk about it could be at the endpoint if we have a restricted domain. So when I look at this graph right here, if I start over here, I'm increasing, I'm going to switch to decreasing, so that's my turning point. That's a relative maximum or min. I'm decreasing, and then I switch to increasing. There's another one. I'm increasing, I switch to decreasing. There's another one. This end has an arrow. This one has a point, which means I have a restricted domain, so I have to take him into account as well. Okay? We all good so far? All right. So then when we talk about them, the values of the maximums and minimums are the y values. They're the outputs. The location is the input. Location is the input, value is the output. So this says local minimums at, and I know it says x equals, but even if it didn't say x, it's at. So where is it? It's at an x value. So my first minimum is right here. It's at -4. I don't think that's a minimum, right? My next one is here at 0. And then I have this. That's going to keep going to where? Infinity, negative infinity, right? Is that a number? No, so I don't get to use it. All right, so then my local maximums. Minimum, so this is a maximum here at -2, and one here at 3. Okay, we good so far? Any questions? All right. So let's talk about our global or absolute. So an absolute or global extrema, it says of all local maxima or minima. So you have to belong to the relative or local extrema club to be considered for this club, right? If you're not one of those, you can't be one of these. It's the local maxima is the great, we take the greatest or the least of the local minimum. Okay, that's your absolute or your global. So when I look at this and I read, I'll mark where our relatives were. Here's where our relatives were. Right, we get that little arrow going there. So the absolute maximum. So I had two relative maximums. This one's higher, right? So the absolute maximum is 2, and that occurs at 3. Okay? Absolute maximum is 2, and it occurs at 3. Everybody okay with that? All right. What do we think about an absolute minimum? Do you think it's at -3? I'm sorry, it is -3 at -4. Look what's happening here. This is going to go lower, right? So this is going to go all the way to -infinity. Is -infinity a number? No, then I don't get to use it, and I don't have an absolute minimum. It would be none. Okay? There's no absolute minimum. There's not minimum. There's not a point I can name, because infinity is a concept that can hurt your brain. It's not a number. Okay, we good? What questions we got? All right, then flip this over. I'm going to give you a minute, and I want you to work on part A. Just answer these 4 questions in part A. You can talk to each other in your group. That's a good thing. All right. Mario, where's Mario? Pointing at him. Okay. What do you think about a relative minimum? I can't hear you. You don't know? Okay. You want to phone a friend at your table? You want to help him out? What do you think? We don't got one. Exactly. Relative minimum. These are both going to -infinity. So this is a none. Okay, Mario, you are also literally the only person in this entire class that hasn't gotten into something. And boy, all you got to do is go into Canvas and click on the Delta Math assignments. Will you please do that for me today? Thank you. Okay. All right. Next, Angela. What do you think about a relative maximum? Where's Angela? Ah, gotcha. What do you think? At 1? Y'all agree with that? Relative maximum at 1? Yes? All right. Good job. All right. Absolute minimum. Ari, what do you think? What? None. Where's Ari? None. Because you got to be part of this club to be part of that club, right? So this is none. Good job. And if you put NA, the directions say NA, I meant to take out none is fine too. Totally fine. All righty. And then Casey, what do we think about absolute maximum?
Sorry, I don't understand.
I didn't say Siri. Okay, sorry. Say it again. 3 at x minus 1. Good. There you go. All right, we good with all that? Yes? Okay, so now I'm going to give you another minute, and oops, what happened? I want y'all to work on B and C. You can talk to each other about it, get some input from your neighbors. Yeah, do B and C. Yeah, B and C. Pretty much, yeah. Or the endpoints, if there's, don't forget the endpoints too. All right, Jermaine, what do you think about on B, relative minimum? -2. Y'all agree with that? Is that the only one there is? Yeah, okay. Thank you. All right, Paulina, relative maximum. -4 and 3, good. Remember, you can't forget the endpoints as well as the turning points. All right, Angel Sanchez, absolute minimum. What do we think? Where's Angel? What am I looking at? Okay, thank you. Absolute minimum, none? Y'all agree with that? Yes, because I had a relative minimum, but this keeps on going, so that is none. Very good. All righty. Casey again. Absolute maximum, what are we thinking? 2 at 3, good. All right, and so just a little side note here. Let's say that this actually kept going and it was like right here, okay? Then my absolute maximum would still be 2, but it would be at -5 and 3. So I still only have one maximum value, but it could happen at more than one spot. It could actually happen in an infinite amount of spots, depending on the equation or the graph. So just know that if they're the same, then I would put, the value is the value, but then you might have more than one location for one. Right? That's a possibility. It's just not on here. All right, thank you. All right. Ari, again, I don't know. It's random, so this is true random. Relative minimum, what are we thinking? -4 and -3? Y'all agree with that? Yep. You sure about that? -3. So I'm changing from, I'm like this one and this one. I agree with that. Okay. This would not be a relative minimum though, because that's going to appear, that would be a relative maximum. So instead, I like -3 and what? 3. Does that make sense? Yeah? Okay, that's all right. Nobody's perfect, myself included for sure. All right, Carlos, relative maximums. What are we thinking? 5, okay. And 0. And that, so here and here. Is that it? One more. You're missing one more. You got this one and this one. What are we missing? Oh, the pink one? Yeah, I probably just here. But look at you, being responsible to come get it. You're welcome. All right, yeah, so -4 also because of that endpoint, right? All right. Absolute minimum. Bray, what are you thinking? Good. -3 at x equals -3. And then absolute maximum. Marlon, what are you thinking? 4 at x equals 5. Y'all agree with that? Yes, good job. Thank you. Any questions at all? We can figure out the maximums and minimums. They make sense? Yes? All right. So now we're going to move on to the fun facts. Now, sometimes fun facts are just that. Like we had one about a roller coaster the other day. But this is a fun fact that we actually need to know. Okay? And we have to be able to apply. So it's an important fun fact, I guess. So between two real zeros, remember we can have imaginary zeros or non-real zeros, and we do talk about them some, but in general, we live in the real number system. So between two real zeros of a polynomial, there must be at least one local minimum or local maximum. Okay, must be at least one. Basically, I have to turn around to come back, right? I have to have at least one. Then polynomials of even degree must have either a global minimum or a global maximum. And when you're done writing that, don't start putting up because we got a lot more writing to do on here. Okay? Because I'm going to basically explain to you what that means and how the questions are going to be asked. Okay? For some of you, the words are enough, right? Words are enough and they make sense. Some of you are like, I have really no idea what that sentence means. So either way, we're going to go through this together. So there's space down at the bottom. We're going to use that space down at the bottom. And we are going to pretend like we've been asked a question. Does this function have a global maximum? Because that's totally a question we could be asked about an equation, not necessarily a graph. With the graph, I think we got that part down. Let's talk about equations, right? So let's say that I give you the equation g of x equals 4x cubed plus x squared minus 2. Right? You don't get to use Desmos. You don't get to use a calculator. You don't have to be an expert on this equation. You just have to know a few little things. You can either, some of y'all will just know it, but I think sketching out little things helps. We're going to do a lot of little sketches. Sketches are not drawings, are graphs. If we're going to graph something, we want it to be like as perfect as we can and nice and everything even. A sketch is just something to get down on paper to help us wrap our mind around what's going on. It's not always 100% accurate or beautiful, but it gets the job done. So if I have, this is an odd degree polynomial. Do we agree with that? So the end behavior models that of a cubic, and this is a positive leading coefficient, so my end behavior should look like that, right? So I'm going to start down here, and I would have at most 3 zeros. So I go 1, 2, 3, okay? Good enough. Now, by looking at my sketch, even though I know it's not super accurate, it's accurate enough with the important stuff that I can answer this question. Do I have a global maximum? No. Do I have a global minimum? No. But notice how I do have at least one relative. That's what that first sentence says. I have at least one between any two zeros, but I only have, but I don't have any globals. And that's, so think about the fact that for an odd degree polynomial, the ends will always be opposite. And if the ends are opposite, is it possible for you to have either global? No, you can't. So the second part there talked about the even. It didn't say anything about odd, but if I have an odd degree polynomial, I don't have either one. So to answer this question, I can just say, so the question is, do we have a global maximum? The answer is no. G is an odd degree polynomial. That's how you know. And I think the sketches can help you sometimes wrap your mind around what's going on. Okay. What questions we got? We good? All right. So then let's say that I give you h of x equals 2x to the 5th minus 6x to the 6th plus 3. Is this an even degree or odd degree? Even, because my leading term is this right here. It's even, so it models a quadratic. There's a negative leading coefficient, so I know the end behavior would be down, down, like that, right? Because that's what would happen with my quadratic. So if I'm going to sketch this, I'm going to start down here. That's 6. So I'm going to go 1, 2, 3, 4, 5, 6. Just like that. Okay? The middle stuff, we're not really that worried about right now. I mean, we are because we're talking about maximums and minimums, but where they actually are, not concerned right now. But if it's got to be down, down like that, then do I have a global maximum? Yes, I do. right? And this is, I mean, my picture, I mean, we could say that I actually have 3. I really just have 1, but it happens at 3 places, or what, that doesn't matter because we don't know that for sure on this one. But so then we are going to say that we're going to say yes, H is an even degree polynomial Now, just saying it's an even degree, that guarantees that I have a maximum or minimum. What makes it specifically a maximum is that it is with a negative leading coefficient. That's how you distinguish between which one you have. Is it opening it up or is it opening down? Okay. What questions do you have? Anything? We good? Okay, so we know how to do it by looking at a graph. This is kind of how you do it by looking at an equation. Probably have a question like that on the actual exam for sure. All right, any questions at all? All right, go ahead and put that in your ISN. I will hand out your assignments.